All right, folks. So we're talking about feature engineering, and we've discussed feature engineering a couple of times with regards to deriving your own columns, maybe collapsing two columns like length and width and turning them into area. That's a very simple example. We could also do feature engineering. Your best source of feature engineering, in my opinion, is getting to know the domain, right? If you know the domain, you have extra depth and richness. And you might know based on that domain, like real estate or something like that, that a property is not going to have zero bedrooms or zero bathrooms, right? So your best feature engineering comes from knowing your shit.
Domains have a lot like context.
Yeah, context. Domain means like your industry, your business, your specific company. Yeah, so that's all context. But it's a specific context, right? So like your domain background may be X and Y, my domain background may be A and B, right? So it is the context, but it's your specific context, right? Or the specific context of your employer or the data itself. Yeah, did that help? Yeah, absolutely, all about context. And it's specific actionable context with domain knowledge, right? Sometimes just the littlest piece of information can save you from doing and having to do things really complicated stuff. Somebody in accounting that you had coffee with just mentioned something offhand one day. Oh yeah, we don't even use that column. That's a piece of garbage that that like some export put in there. Oh, well, I didn't even know, right? So always get to know your domain is my punchline. And you can forget everything you know about slip covers, but remember everything you know about data exploration. So what the heck am I going to teach you today? I'm going to teach you two different tools for feature engineering. One is statistical in nature, and that you would use this when you don't have all of the data and when you want more of when you want information about your features from a more statistical standpoint. That's called SelectKBest. That's more stats oriented in nature. It's actually using hypothesis tests underneath the hood. The other tool is called recursive feature elimination. And what that means, that's a fancy way of saying you train the model with all the features, see how it performs, train the model with less features, see how it performs, train the model with less features, see how it performs. Okay. So again, no substitute for domain knowledge, but if we want a nice way of understanding from either a statistical perspective or a modeling perspective where our more informative columns are, these two tools are going to help you with that. I'm going to introduce two tools here. You don't need to use both of them. In fact, I mean, you don't have, there's nothing that says you have to use these tools at all. I mean, I might double check the rubric on the next project, but you don't need to do both, right? They serve the same purpose. You may see the same columns. You may see agreement between the stats approach and the modeling approach. That's a really good indicator that those are good columns. You may see disagreement between the stats approach and the modeling approach. And oh my God, what do? Pick one and move forward, right? Or use the features that are suggested by both if you happen to do both, but you don't really need to do both. I think you will for the exercise, but in practice, just pick one and roll. All right, so I'm gonna do my imports. Nothing new on the imports yet. Just NumPy, pandas, and I'm going to read a CSV here. All right, so our first tool that I'm going to introduce to you is called SelectKBest. All right, and SelectKBest is coming from sklearn. sklearn has a module on it called feature selection. That's where both of these are going to come from. And I'm importing SelectKBest and F-regression. So F-regression is the, we didn't talk about this specific in hypothesis testing, but it is handling the hypothesis testing underneath the hood with SelectKBest for us. And what this is going to do is find out which of the X's have the strongest relationships with the Y. So independent variables with our dependent variable. And we can control that K, just like with other things so far we've seen in data science, like K nearest neighbors, we can control that K variable, right? So if we say, give me the top 2 features, your K is 2. Give me the top 10 features, the K is 10. You can't have a K higher than the number of features you have, right? Obviously. So how in the heck do we use SelectKBest? It's quite easy, actually. With so many things in sklearn, whether if it's a scalar or a model, we really have a 3-step process. You make the thing, you fit the thing, and you use the thing. So that process, that's the process of the sklearn designers and developers built into the API, such that you can, if you don't know anything about a random forest, you still just make the forest, fit it, use it. Just like you would make a decision tree, fit it, use it. So same thing, here is the mechanics of what we're gonna do. We're gonna import SelectKBest and F regression. Now that first step, the make the thing step, we are going to say, hey SelectKBest, I want to use an F regression as the statistical tool here, and give me the 8 best features. That's what that K argument here is. If you wanted to get fancy, you could put that K in a loop and run this across a couple of different Ks, right? So we make the thing. This is an empty object right now. All it knows is that it is supposed to evaluate using F regression, and its K is 8. Now we're going to fit that thing. So make the thing, then fit the thing, and then we can use it. So fitting the SelectKBest, we feed it the scaled Y or the scaled X's and our target variable. Very similar to what we would feed into the model. And then what we're going to get back from this is the F selector object, once it's fit, and runs all those statistical tests, this get support function is going to give us back a whole bunch of Booleans. So I'm going to run this cell, and what's going on is that Boolean mask is turning on or turning off columns if based on the output of the statistical test from that F regression. So that feature mask is an array of Booleans. That's what get support is going to do. It's going to say, oh, bedrooms, important, keep them. Bathrooms, important, keep them. Air conditioning type, not important, don't keep it. Or whatever the issue is. I'm not trying to tell you that that's a punchline anywhere, but bedrooms and bathrooms is probably a good predictor. And then what we're doing with this iLook right here is we're saying, hey, give me all the rows, but filter out that feature mask. So just the columns, just those 8 columns that were informative. So I forget the data that, the data that we're looking at is some math grades. There we go. Pretty sure. So let's run that. And then what we get back, oh, this is different. Let's take a look at our initial data frame here. Just take a look at the first like 3 columns or something. I don't think y'all have seen this data yet. It is schooling and test information. There's a whole bunch of demographic stuff on here, all kinds of different test scores across here. And this is a 49 column situation. So this is a good time to pull out, yes, data can get large. Yeah, 49 different columns, explanatory columns. Data can get very large. So in this place, it might not be useful to make a model with all 18 features. Hence our new friend SelectKBest. And we're gonna just pick 8. And what this gives us back is age, MEDU, FEDU, travel time, study time, failures, G1 and G2. So G1 and G2 are different. They're like a midterm in a quarter term test. If I understand this data correctly, how much travel time that student has. I can't remember what MEDU and FEDU are. Oh, there we go. Yeah, the mother's education, the father's education. Cool. So if we were to say, hey, give me the only best, a K of 1, we get back just the G2. Well, what about K of 2? It's G1 and G2, right? So we can get a little bit of an understanding of what are the most important. If we only can model on 3 features, or if we decide we want a nice small amount of features for our first model, select K-best with the K of 3 gives us the 3 most important according to the F regression. Yeah, right.
Now, under the hood, is it also checking for collinearity to see if, it's basically looking at the same, if these are.
I don't think so. I don't know off the top of my head. I mean, we could check the select K-best docs, but I don't think it'll speak to collinearity. Let's take a look at the docs anyway, because it's always a good idea to take a look at the docs. Selects features according to the K highest scores. Our parameter is the score function. That's where we sent in that F regression. Defaults to 10 if you don't pass something in. Scores our features. These attributes, so the parameters are what you're sending the select K-best function. These attributes are what we can get out of it. So we could get out these scores. So we could say F selector, because that's the trained select K-best. I could say dot scores underscore. And the order of these is going to match the order of what we've of all of the columns. And we don't really do anything with the scores ourselves. If you wanted to get the p-values, you could as well, right? So p-values underscore. Right, so some of these have a really low p-value, 85 to the negative 85, right? 5.5 times 10 to the negative 85. That tells us that the G2, the G1 have a lot of predictive power, right? Now we're getting back from the p-values, we're getting back a p-value for every column. And so this get support is really just doing a cutoff based on your K argument. You look like you've got a question.
Almost.
Okay. I don't need to put you on the spot if it's still forming.
Oh, no, it's
Yeah.
perfect. So we started out with 49 columns and now we have what looks like not 49 values.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I don't know. I was expecting one from everything. It defaults to 10, but we're seeing more than 10 in the p-values.
It's like 3, right?
And my K was 3, yeah. Mysterious mysteries. Yeah, I don't know. It doesn't speak to that in the documentation either. It's a little light, actually. There you go. I love that curiosity. And let me look for multi. Yeah, I don't see collinearity on here. Jen?
Just really quick, can you remind us on this data set what the Y is?
Yeah, let's figure out what our Y is. I totally forget. It's probably the grade. Whatever that column is. Yep. G3 is the final. So this is saying that the G2 and G1 are very informative for the G3 final. And if we were to crank our K up to like 10, or I'll set it back to 8, each one of these is contributing. Those are statistically significant, but the order is going to be from the right to the left as far as what's important. I don't know why they did it that way. But you can confirm that by making a smaller K. Yeah, that's really it. That's really it for our select K-best. I'm not going to do a lesson itself on F regression. It's a good hypothesis test for either categorical and continuous variables in this case. And we can put a reasonable amount of faith in this. So this is statistical based, right? This is a hypothesis test. And it's a one or the other thing. I'm going to introduce you to the cousin or the sibling here, is recursive feature elimination. So this one is not stat-based. This one is actually making a model, making many, many models. And so here's what's going to go down. We make the thing, fit the thing, use the thing. That's our larger overarching pattern. But let's talk about these words. What does recursive mean? Not really. Kind of, but not really. Something that's defined in terms of itself, right? The song that never ends is defined in terms of itself. It goes on and on, my friends, right? And then you get to the last line and then you say it's a song that never ends. So recursion means doing things over and over again. It's very similar to looping, but instead of a loop, it's a function that calls itself for a piece of data that's defined in terms of itself. We have a lot of recursive data structures on the planet, and in data science, the easiest one to think of is your bill at a diner. You walk in, your bill's $0. You order a tea, the bill then is tea plus what it used to be. You order fries, it's tea plus what it used to be, plus fries.
So like recursive, like reoccurring.
Yes, like reoccurring, yeah. Recursive, yeah, recurring. So to recur means to recurse again. Yeah, absolutely. So here's what's going to go on, and here's what recursion has to do with this feature elimination. So RFE creates a model with all the features, every feature possible, right? Then it evaluates the performance metrics, finds the weakest feature of that set, removes that weakest feature, and then it recurs. And then it creates a brand new model with all of the features minus the weakest one. That's the recursion here. Then we run that model, evaluate all the performance metrics, find the next weakest feature, then remove that. And so on, and so on, and so on. It could possibly take a long time. So we're making a model based on all columns. We have 49 columns here. If we have 1 million results, this might run all night, potentially. I think I saw Fred's hand, and then I saw a question from Arsene as well. So we'll hear from Fred.
The ranking that produces and Saudi for the citizen sector, just want to show us what the ranking produces. Can that give us some descriptive statistics of the ranking about the performance of that model? Slowly eliminating the top.
What we get back is a ranking of those names of the columns. We can get the number of features. It's not telling us the metrics for everything. Yeah. Otherwise, it would be a listed attribute in here. So just as an, oh, by the way, parameters are things, I know I said this a minute ago, but parameters are things you say they're going into the function to train a model or to train, and this is a model, right? Attributes are things once the model's trained, you can ask the model about itself. And I don't see that we can get the metrics themselves. Yeah. I saw a question from Arsene. I think you had your hand up. Go ahead.
Yeah. So what would this, because I know we're in the exploration phase, but what would this be? How would this be different from modeling?
Well, this is different from modeling because RFE isn't going to give you a model at the end. It gives you a list of columns at the end. Okay. It is modeling underneath the hood. That's where it's doing all the modeling. And this could be a runaway train if you have tons and tons of columns, millions and millions of rows, and and you run this, it's gonna get your processor a little warm. But the place, it's kind of weird where feature engineering comes in. You might notice in the wrangle and as you're summarizing the data that you might want to do some feature engineering as far as combining columns or splitting columns apart or bringing in domain information, domain knowledge. You might end up doing some feature elimination inside of Explore as well. So it's also the case that you might run through the pipeline and then on your second draft, do some feature engineering. So there's a place where feature engineering could live in multiple parts of the pipeline, right? I know, I wish I could give you all a paint by numbers, everything's linear, but it's not. And if it were, it'd be a function, not a job with upward opportunity, right? Yeah, but RFE isn't going to give us the model. It's going to give us the columns that we should then put into another model. Did that help, Preston? Cool.
If you did.
Yeah. See a question from Kate. Go ahead, Kate.
Yeah, just to make sure I understand, and I know this is more pedantic than anything, but is feature engineering just the creation of new columns technically, or does that feature engineering also include feature elimination?
It also includes feature elimination. So feature engineering, broadly defined, could be dropping columns, adding new columns, taking a column that actually has like that should be three columns. Like maybe there's an address column and it has the information for zip code and state and the street address. That might be more appropriate as three columns. That I would consider that also in the realm of kind of feature engineering, a little more data prep. But
Would that mean the final result of feature engineering would be the exact list and format you want to plug directly into your model?
Yeah. Really, I mean, features are the columns that we train the model on. So anything that changes those those columns, whether if, I wouldn't say renaming the columns as feature engineering, but building a derived column or a synthetic column or eliminating columns, that's all fair game for feature engineering. I often use this example of if you have length and width, you can get area. But let's say the domain that you're working with is much more complex. Maybe the domain you're working with is biochemical, right? And maybe you know something about those columns where when A shows up and X shows up in the same column, you have some knowledge that it's going to imply C. And you can then say, okay, 99% of the time, and that's just not in your data set, right? You'll be able to use what you already know to inform the data set, right? I'll give you an example of domain knowledge helping you to build a column. A little bit later in the course, y'all are going to be working with anomaly detection, and y'all will actually get the opportunity to look at curriculum access logs, right? To look for weird stuff. And in those curriculum access logs, just based on my domain knowledge, being in CODA for a handful of years here, I could tell you before a certain date that all of those observations are definitely web dev students. Just because I know when data science started, right? February the 4th, 2019 here. So that tells me that any request to the curriculum that came on or before that date does not include data science. It does not include the CODA Cloud folks. So I could make a column right there that just helps me identify that nice and early. Does that make sense? How anything where you can add a column, delete a column, or split columns, or anything that kind of changes those is really feature engineering. Yeah. Thanks for that clarifying question, Kate. Yeah, Fred.
Just for rule of thumb, what you're building synthetic columns.
Yeah.
So let's say you have some domain knowledge, or potentially you just build some insight.
Yeah.
Data. You said make separate data frames that have kind of your own kind of swing of things versus like adding your data frames. So you're not.
Oh, I see what you mean. I'll glom them on because usually if I know something extra that's informative, that should be a feature. And that's kind of the punchline. I might peel off a data frame like a subgroup, like the LA County and investigate just LA County on its own. But I wouldn't make I don't want to give a hard and fast rule, but I wouldn't want to, unless I knew something extra valuable about just one county, I wouldn't add a column to that FIPS's data frame rather than another ones. But you could. Yeah. Cool. So something that's important to know about RFE is it can work with other kinds of models that I'm going to demonstrate for you today. I'm demonstrating the linear regression model, but RFE could use a classification model or another type of regressor. So maybe your RFE tells you one thing on a straight line linear regression, but it will tell you something else depending on the data if you send it a polynomial model, right? Or another kind of regression. Or if you have a different target variable that's categorical, you can do classification with RFE. So let's go through our steps. Initialize the machine learning algorithm. So we have to make a blank ML algorithm. This is one more step than that usual, make the thing, fit the thing, use the thing. So we make an empty model for what we're going to use. Then we initialize the RFE object, and we send in the ML model that we decided to use as an argument, as an input. We fit the RFE on our data, and then once we fit the RFE, what we get back out of it to use the RFE is we get back that list of features. We can get back the rankings. So let's check this out. We can get the rankings of our variables, and the ranking of 1 is the most important. So let's take a look at the code. I'm saying from sklearn linear model, excuse me, this is how you'll import linear regression when you're ready. And actually the code we're looking at with RFE here is more complex than just making a linear regression, right? If you just made the linear regression, we just make it, fit it, make predictions. So we're going to initialize an empty ML algorithm. So we're accepting, in this case, there's no inputs going into this linear regression. So we're accepting all the defaults. So sklearn linear regression. We'll do the linear regression lesson on Monday. But we're moving forward with all the defaults, which they're all pretty healthy for a linear regression. It's just a straight line. We're going to import RFE. So we make the linear regression and then store that to a variable called LM, or something that's descriptive rather than X, right? And then we call the constructor function for the RFE. We send in the linear, whatever model. It could be polynomial, it could be another type of regressor, it could be a classifier. And then we specify the number of features to select. So we can select less features than we have. We can select the same number of columns that we have in the original data frame. This will generate that RFE object. Then we fit the RFE object. So this process of fitting here is going to run the linear model that we provided on all of the features, get rid of the worst feature, run it on everything but the worst, then take out the worst feature and keep on going until we hit the number of features to select parameter. It's really cool. And it is automated feature engineering. It's telling you what to toss or what's important. In order to get the Boolean mask for what columns we want to turn on or turn off, we call RFE.support_. That gives us a list of Booleans. We use that list of Booleans in a loc, an iloc, or a subsetting syntax to say, hey, show me the features. Show me the columns that it listed. And so when we run this and we focus on the 2 best features, RFE is telling us G2 and G1. That's nice because it's in agreement with the statistical hypothesis or the statistical feature engineering function. But this is actually running models, right? Now, one of the reasons why it's not a good idea just to automate all your stuff initially, what if you're feeding a linear regression, a straight line model, and the relationship between your input variables and your target is curvilinear, is a polynomial, right? Then this isn't going to be magic. This is why you can forget everything you know about slip covers, but don't forget everything you know about exploration. Yeah, Jules, what's on your mind?
Okay, because I thought so in this step, this is like, you wouldn't do this, or would you do this before you did EDA?
I would not do this before EDA at all.
But after, okay,
Yeah,
so-
I would do this either at the end of my EDA. I kind of want to confirm what I've found almost. And one reason, a very important reason why I would not do this before exploring the data is I don't know what kind of model I should put in here unless I have some understanding of the relationship between the X's and the Y's.
Follow-up question.
Yeah,
Because
yeah.
When you scale data, you're scale the data, and so you're able to use it at that point because you haven't used it on the EDA itself. Like, is that the end? Because I thought we weren't supposed to use scale data at all. Like,
Oh, for exploring. The reason you don't use scaled data for exploring is because it doesn't make any sense to human beings.
right. So as long as it's after you're done with your EDA to confirm something, it's okay then.
Oh, to use scaled?
Yes.
Yeah, yeah. Like you could certainly explore scaled data, but it's not going to make the units won't make sense. The shape of the relationships will make sense. If you use a linear scalar, the shape remains the same. Yeah. So check this out. The next little, I really want to show this part to you. So we get all of the rankings, we get the variable names from our original data frame, and then I'm going to make a data frame here that shows us the variable name and the rank. And I realized that we only set a number of features to select as 2, but this ranking is going to give us a whole bunch. I don't know why it's giving us 14 instead of 49.
Related to that same issue.
It's that weird ass same issue, which is, I don't see in the documentation. But that's pretty cool. So this tells us, even if we only told it the first 3 features or whatever, this line of code or this cell block of code can give us more information.
Now, is G1 and G2 the same rank because you chose to use both of those? Because you chose your top 2? Or is it just because they were equal and could differentiate between the 2?
That's a really insightful question, Ryan. Let's double check. I'm going to change my features to select to 3. Yeah, that's why. Yeah, did I see a question from Arsene?
Yeah, it was the same question, but I don't know how he framed it. So I don't know what your answer meant.
Yeah, so if I say 1 feature to select, the rank is 1. If I say select 5 features, it's the first 5 features here.
Got it. Thanks.
Yeah. And what else do we have about this? sklearn, RFE. So from the trained RFE, we can get the number of features. We can get those feature names, the ranking, and then support is what's giving us that Boolean mask. And yeah, the selected features are rank 1. So that's pretty cool. The rest of the curriculum here is a little bit longer version of the same stuff. So I'm happy to walk through that with you. Again, you don't need to do KBest and RFE. It's pick one that's appropriate for the situation. If you have a ginormous amount of data, my recommendation is to use the statistical approach with KBest. Like, I mean, a lot, like millions and millions of rows. If you don't have all of the data that you would have, like if you're sampling, right? If you're sampling a data set, I would encourage you to use KBest since it's statistical in nature, right? So a nice little review. We make the thing and we set as a hyperparameter the K. We fit the thing. And what I'm, let's see. We're transforming our data set, okay? So because I said K of 2, this X reduced only has those 2 columns, right? So let's check out X reduced dot head. It's not a data frame. It's a NumPy array. Okay, but it's only those 2 columns of G2 and G1. Yeah, Arsene, go ahead.
Just when you talked about the difference between the NumPy array and the data frame, that I remember the question that I had for a bit of a time. How do you take a non-pi array that you already have, that already exists, and then you transform it into a data frame? I've tried and then it didn't work.
You wrap it in a data frame constructor. Now this begs the question, where the heck do we get our columns from, right? We're gonna get our columns from, we have to say fSelector dot SelectKBest. Let's get one. Let me pull up the documentation. No. Let me find that. The get support function.
Okay.
So
So
to
the
answer your
mon-
question, yeah, to answer your question, the way you get a data frame is you use the data frame constructor, but
Yeah,
that's the whole story, right?
yeah. I mean, there might have been a problem with the data that I had because that's what I did, and the error that it gave me is that it can't do it because it's not a one-dimensional object.
If you're getting a cannot fit the model because of a one-dimensional issue, then you
Yeah.
take whatever your thing is, like an
Mhm.
X, and you wrap it in a data frame constructor like that. A data frame of one column is not the same thing as a series. And that's probably, was this something from the exercise maybe?
Yeah.
Yeah. You wrap the data frame constructor around that one series is your answer.
Okay. All right. Thanks.
And how we could get the columns here. So this is telling us that we have a feature mask here. So I'm going to go back and steal from my own code here. We're going to say, there we go, grab that, back down. Take care, Fred. Hope you have a great afternoon. And how do I turn this feature mask to actually get those? Is I'm going to use the either loc or iloc to filter out the columns. And we'll see what we have here. So let's see. This is coming from xtrain scaled, feature. And so I have G1 and G2. This means that in this data frame constructor, I can say columns equals F feature. And the order of this is going to work out for us here. Oh, that's a variable, not a string. There we go. Cool. The next little line of code tells us the same 221 rows, 2 columns left over. And if we want, we could use inverse transform here to return the original variables. But yeah, this is pretty helpful stuff, right? We go back to our basics, array of Booleans. How are we getting the array of Booleans this time? From the fSelector get support. That's going to give us a true or a false based on if that column was statistically significant based on the number of K that you passed in. Okay. Pretty cool stuff. And recursive feature elimination, again, just to recap, you do your appropriate imports, you import whatever model you're going to have RFE run. Again, this could be a decision tree. This could be another kind of regressor. Then we instantiate that empty model. And if your model has other hyperparameters, you tune those other hyperparameters. So I know some of y'all were making some for loops to for loop through a bunch of different hyperparameters. You could really set your laptop on fire by iterating through every hyperparameter option and running RFE. Right? But hey, I'm sure Amazon wants you to do that once you get the company credit card signed up to Amazon. Question?
Kind of related question.
Okay, yeah,
If you have a, say, a spare backup tower at home that has more CPU, would you be able to run these programs faster?
well, yeah. Yeah, faster computers compute faster. Yeah, absolutely. Yeah, for a long time and still, and yeah, and I don't say that it's obvious, right? Getting cloud computing to do GPU processing has, until pretty recently, it's been very challenging to virtualize GPU processing. CPU processing, cloud's been doing great for decades, right? And you can horizontally expand it and turn up, oh, I want 100 processors in this virtual machine, right? But for the longest time, a lot of folks were reluctant. When I say folks, I mean institutions, businesses who know what they're doing and have the resources, they would prefer to buy desktops for their machine learning engineers and their data scientists because running the stuff in the cloud was expensive, real expensive, right? That only makes sense if you have the need for speed and the need for scale, right? So if it's okay if your model takes all night to train, just train it on your desktop. And if the business is okay with that, that's totally cool, right? So like a lot of deep learning and other classical ML, like we're learning here, happened on desktops instead of in the cloud for a long time, until kind of recently. It's just more expensive. Just like a FedEx truck full of hard drives is an effective way of getting more terabytes across the nation than the internet, right? It's different, right? It's a little different. But yeah. So you make the thing, you fit the thing with the model that it will fit for you. You fit your RFE, and then get your Boolean mask. Once you have your Boolean mask, you can get your list of features. And if we want all of it, not necessarily all, but the first 14, still don't know why it's defaulting to only 14, but I'm sure there's discussion about this in the sklearn source code on GitHub. But it's not too bad. So and we might want to sort this on rank too. Right. And by might, I mean, we definitely do want to sort that on rank, right? So it's pretty handy. Again, so automated feature engineering, this doesn't absolve us of the need to explore the data, but this is a really nice to have if you've explored the data and say, okay, I've got a bunch of features that look promising, and you want to run a model on a bunch of those features and see which ones are the first 3 most important, first 10 most important. And there you have it, folks. RFE and KBest.
During a presentation, is it good practice to kind of show your exploration and then show that you ran the system? Kind of like this also ridiculous.
Depends on the audience and your deliverables. This probably isn't going to make it to a slideshow, right? However, the ranking here might, right? Some of these columns might, like, hey, the top 3 are the early midterm, the second midterm, and then the number of absences. Those are our best predictors according to my analysis. You don't have to go into it according to RFE. And KBest said something else. Like if you're on a slideshow, just keep it real simple. I noticed a handful of people did correlation on the telco and provided the correlation coefficients. Again, that's kind of challenging with binary columns and categorical stuff. But this is actually telling you the feature importance based on the model. And if your model isn't a regression, if it's a classification, RFE is going to work the same way and get you the same kind of output. It's really cool. But you do have to know your data. You can't just say, oh yeah, linear regression, all the things. Right? Yeah. Pretty cool stuff. So you might run both an RFE and a SelectKBest and get agreement. You may get disagreement, but you got to keep in mind one's statistical, one's model-based in nature. So if you're not choosing the right model that matches the relationship or even approximates it, you could dig yourself into a hole here. Okay. So forget everything you know about slip covers. Remember everything you know about it. Explore, and also put this in your toolbox, right? You can live perfectly happy, a perfectly happy data scientist life without these two tools. When would you use them? Maybe on your second draft, right? Get through your first draft first. Cool. So that's what we got for you. It is it's 3:40 on a Friday. No, we're not going to roll in a TV and just watch Star Wars the rest of the day. I do want y'all to work on these. However, if you are not finished with the previous exercise or need to do any other work on your Explore, or even if you have a to-do to go back to your Wrangle, I want you and need you to prioritize that, because next week is project time, right? Which means that today is also project time, not kind of blow off time. So with that in mind, I am making the executive decision to make these exercise sets for feature engineering are going to be totally optional, right? They're optional if you need to go back and shore anything up. Right now is the time to figure out like, if you felt like, damn, I needed more time to explore the data. You've got an hour and 20 minutes if you need to explore the data a little bit more. The exercises are listed here on the tips data set. If you want to work through these, feel free to, like I said, work through these if you are all caught up. If you're not all caught up, shore up and do that backfill. And it's your call if you want to work on the tips data set, or if you want to pull in Zillow. Just remember, this running Zillow 2 million rows on Zillow data is going to take a little while. So if you hit run on a cell and 30 seconds passes and you're like, Ryan, it's broken. It's not broken. Yep. That's what I got for you, folks.
It's kind of a follow-up